Hello, everybody. Good afternoon, and welcome to our inorganic chemistry course. So today, before we start, we have a couple of announcements. So homework 3, according to the instructions, was due on Monday, December 6th. However, when I prepared the homework and then I thought about this due date, I forgot that December 6th is actually a holiday here in Finland. Therefore, like the first thing is that we will not have class on Monday, December 6th. So our next lecture is only next Friday. And also, because the homework was due on December 6th, then I'm going to give you guys one more day to return the homework. So homework 3 then is due instead of Monday on Tuesday until 6 p.m. Okay, so you guys have one more day to turn in the homework. And I'm gonna write that in Moodle as well, so that everybody knows about it. All right. So sorry, I ended up forgetting about that Monday was a holiday. All right. So also we will be starting today coordination compounds, which is the last part of our course. So we will have 3 lectures on coordination compounds, and then we will have an exam. So for coordination compounds, because this is pretty close to when we finish coordination compounds, we will be pretty close to the exam already. So what I'm gonna do regarding coordination compounds is that I'm gonna post a homework comprising coordination compounds. I posted this today already. So, but because we will be studying coordination compounds and it's gonna be very close to the last day of our lecture or the last day of lecture or the last day of our course. So because of that, the homework for coordination compounds, you guys don't need to return. You can just use the homework as a study guide to prepare yourselves for the exam. So I already posted on Moodle, actually, the homework for coordination compounds, which is homework 5. And then for that one, you guys don't need to return. You just use this homework as a study guide for the exam, because by the time that we finish coordination compounds, the exam is going to be pretty close already. And also, I just posted today the homework number 4. So homework 4 is going to be about solid state chemistry, which we study in the last three lectures. And this homework 4, this one you guys have to turn in, and the deadline for turning in this homework, it's going to be our last day of our course or the day of our exam. So homework 4 is due December 17. So summarizing, homework 4 is on Moodle today, due December 17th, which is the day of our exam. And homework 5, comprising coordination compounds, is also on Moodle already, but in that case, you guys don't need to return that homework. You can just use as a study guide. So does anybody have any questions? It seems that no. All right. So with this, then we can start our lecture of today, in which we will begin our discussion on coordination compounds, which then comprise the last part of our course on inorganic chemistry, in which we will be discussing several aspects of coordination compounds. And we will start today with a brief or an introduction about coordination compounds. Basically, we will discuss what is coordination compounds, what is coordination chemistry, what is the language of coordination chemistry, or how the nomenclature of these compounds work. We will discuss the constitution and geometry of several coordination compounds, the possibility of isomerism and chirality, and also we will mention and study the thermodynamics of complex formation, which involves the synthesis or the formation of a coordination compound. All right. So when we talk about coordination compound, so the name coordination compound or a metal complex is very often seen in inorganic textbooks and also in the inorganic chemistry literature. All right, so what does the term metal complex or metal complexes mean? Actually, when we talk about a metal complex, we are talking about a compound in which we have a metal atom or a metal ion surrounded by several ligands. So a metal complex is simply a compound in which we have a metal atom or a metal ion surrounded by several ligands or bound or forming bonds with several ligands. And this kind of compounds play an important role in inorganic chemistry. And the term metal complexes the term metal complexes come from the fact that during the discovery of these compounds, the structure and the bonding could not be predicted or described using the established or the established octet rules for bonding. So this is why it was very puzzled or was very puzzling in the beginning during the discovery of these compounds to be able to investigate and describe the geometries and the occurrence of the several types of compounds that were being observed. And these elements are especially occurring and they are especially important when we are talking about metal atom or ions comprising the D block. So here we will introduce some of the common structural arrangements that these metal complexes have, or the common structural arrangements for the ligands around a single metal atom forming this complex, and the specific or the different types of isomers that are possible from these in these common structural arrangements. So once again, here the term complex means simply a central atom or ion surrounded by a set of ligands. And a ligand comprises an ion or molecule that can have an independent existence, such as chlorine, water, ammonia, and so on. All right, so examples of complex. An example of a complex is this type of molecule, for example, in which we have cobalt-3 ion surrounded by 6 ammonia ligands. So in this case, we can say that we have a complex in which we have the metal surrounded by 6 different ligands. Okay, so this is an example of a complex, and then in each position here we have the ammonium ligand. Okay, so this is an example of a complex. And the term the difference between a complex or a metal complex and a coordination compound is that we use the term coordination compound when we are meaning, we are talking, or when we refer to a neutral complex or an ionic compound in which at least one of the ions is a complex. So coordination compound refers to a neutral complex or a ionic compound in which at least one of the ions is a complex or contains a metal ion or atom surrounded by 6 ligands. Therefore, if we take a look on what a complex is, this molecule, for example, we can say that a complex can be regarded by a combination of a Lewis acid, which is the central metal atom, with a number of Lewis bases, which are the ligands. So let's remember the definitions of Lewis acids and bases that we saw in our acids and bases lecture. So our Lewis acid is a species that can receive electron pair or electron density, while a base acts donating electrons when a bond is formed. So here in this metal complex, we can regard the formation of these compounds based on acid-base interactions, in which the metal acts as a Lewis acid, receiving electrons from the ligands that act as Lewis bases. All right. So the atom in the Lewis base ligand, or on the ligand, that forms the bond to the central atom is called the donor atom. So in the case of ammonia, is the nitrogen atom, because this is the atom that will donate electrons to be used in the bond formation by this acid-base Lewis acid-base interaction. All right, so when ammonia acting as a ligand, we have that nitrogen is the donor atom. And as we are talking about acid-base interactions, the metal atom or ion is the Lewis acid in the complex, is the acceptor atom. So in this case, it's important to observe that all metals from all blocks in the periodic table can form complexes. And actually, the main features and the geometrical structure of these complexes were identified only in the late 19th and early 20th centuries by Alfred Werner. And actually, Werner was very creative and combined the interpretation of optical and geometrical isomerism, pattern of reactions, and conductivity data in order to unlock or unravel the structure of these compounds. So actually, they could not use the simple bond theories that were known at that time. Those were not enough to explain like the optical and geometrical isomerism, the pattern and the reactions, the conductivity or the conductance data that they were observing for these compounds. Therefore, he had to be very creative to come up with a model to explain the formation of the observed metal complexes. And this was a remarkable example on how to use like physical and chemical evidence very effectively and imaginatively to describe coordination compounds. And because of this, Alfred Werner won the Nobel Prize in 1913 due to his work on metal complexes and coordination compounds. So this was very amazing, actually. So if we are talking about like a complex, so metal atom or ion surrounded by ligands, this can also be referred more precisely as an inner sphere complex. in which we have the ligands attached or bound directly to the central metal atom or ion. So in this case, the ligands form the primary coordination sphere of the complex, and the number of ligands is called the coordination number of the central metal atom. So the number of ligands directly bound to the central metal atom dictates the coordination number of the central metal atom. So the coordination number refers to the number of ligands that is directly bound to this metal atom or ion. And of course, when we have these inner sphere complexes in which we have the metal directly, or the ligands directly forming bonds with the metal, these are inner sphere complexes, but we also should keep in mind that complex cations can associate electrostatically with anionic ligands without displacement of the ligands already present. And then this association, or this electrostatic interaction between a complex and that ion can form an outer sphere complex, such as this example here, in which sulfate, the anion sulfate, is interacting with this cation, which represents the complex containing manganese and 6 water molecules acting as ligands. So this is a water sphere complex. All right, so regarding metal complexes and coordination compounds, a large number of molecules and ions can behave as ligands, and a large number of metal ions can form complexes. Some ligands display only one atom that can act as the donor of electrons to form the bond by acid-base Lewis interactions. Therefore, it has only one donor metal atom, and therefore only one point of attachment or bonding to the metal. So these ligands are called monodentate because they have only one point of attachment to the metal. But also we can have ligands having more than one donor atom. Therefore, they can have more than one point of attachment, and then they can be classified as polydentate. And in this case, if it has 2 points of attachment, they can be called bidentate, those with 3, tridentate, and so on. And here, in this table, we have like several types of ligands that are representative in coordination chemistry. So all these molecules can act as ligands, forming coordination compounds or metal complexes. So here we have their names, their formulas, the abbreviations used when writing the formula for metal complexes on coordination compounds, and the number of and who are the donor atoms and the number of donors. Okay. And then here also the prefixes that are used for naming complexes, and we will see very soon, like in this lecture, how the nomenclature of these compounds is done. All right. So this I mentioned that we have monodentate and polydentate ligands, but we can also have ambidentate ligands, which means that the ligand can have more than one different type of donor atom. So the polydentate, we have 2 or more donor atoms that can bind to the metal in a complex. In the ambidentate, the nature of the donor atom can change. So one example is the thiocyanate ion, which can attach to the metal either by the nitrogen atom or by the sulfur atom. So the ligand is ambidentate because it can have different types of donor atoms. So both nitrogen and sulfur can bind, can attach to the metal atom. And then also when we are talking about polydentate ligands, an important thing is that polydentate ligands, they have more than one point of attachment, 2 or more, so they can produce a chelate or a complex in which the ligand forms a ring that includes the metal atom, such as in this example here. So this ligand has 2 donor atoms, which are the nitrogens here. So we have 2 points of attachment to the central metal atom or ion, and this leads to the formation of a ring containing the metal atom. Okay, so we will see that this kind of complexes are important, and the formation of these rings is thermodynamically favored as compared to the formation of monodentate bonds or complexes with the analogous monodentate ligand counterparts. All right. So the naming of coordination compounds is important. So it's nice, or it's important that we briefly talk about the nomenclature of coordination compounds. So in coordination compounds or in a complex, the cation and anion are named according to a set of rules. So cations named first, and then ligands are named after in alphabetical order. So for compounds containing 1 or more ions, cations is named first, followed by the anion, regardless of each ion is a complex, because then in this case, the cation can be a complex and then the anion cannot, maybe it's not a complex, and vice versa. So the complex ions are named with their ligands in alphabetical order, ignoring any numerical prefixes. And then the ligands names are followed by the name of the metal, with either its oxidation number in parentheses, as like in the complex that we saw. So we have here the name hexaamine cobalt 3, or with the overall charge of the complex specifying in parentheses, such as hexaamine cobalt 3+. So it can be both of these ways, all right? So the suffix "ate" is added to the name of the metal in the complex if the complex is an anion, such as in this species here, we have tetra, chlorido, platinate, 2 ions, right? Because here platinum is 2+, and the overall charge here of the complex is 2-. But here, this 2 comes from the oxidation state of the metal. Some metals, such as iron, copper, silver, gold, have anion names that derive from the Latin form of the element. And the number of a particular type of ligand is indicated by mono, di, tri, tetra, as we saw here, tetrachlorido, or as we saw here, hexaamine. Okay, and the same prefixes are used to state the number of metal ions when we have complexes that have more than one metal. So in this case, for example, we have octa, chlorido, G, because we have 2, renate, 8, because it's an anion, 3, because 3 is the oxidation number here of the element. And then here, for naming the ligands, we have the name of the ligands here can be found in this table, and it's not necessarily intuitive. So for example, chlorine ions, the name of the ligand comprising chloride ions is the ligand chlorido. For this ammonia molecule is amine. Water, the name of the ligand is aqua, and so on. Okay? So that's why here we have hexaamine, cobalt 3, for example. All right, and also we can have like sometimes confusion with the names of the ligands can be possible, because sometimes the name already includes a prefix, such as the ligand 1,2-diaminoethane, for example. Therefore, in these cases, we can use prefixes of the type bis, tris, tetra, and so on, with the ligand name in parentheses to avoid any type of confusion. For example, if you are talking about dichlorido, this is unambiguous, but tris 1,2-diaminoethane shows more clearly that there are 3 diaminoethane ligands, as in this complex, for example. So another thing about nomenclature is that we can have ligands that bridge 2 metal centers, in this case, and then when this happens, a prefix mu is added to the name of the relevant ligand, as in this example is the mu oxido bis pentaamine cobalt 3. So see here that we have pentaamine. So if we have G pentaamine, would be like strange. So in this case, we can use bis pentaamine cobalt 3, because then it becomes more clear. All right. And then if we have the number of bridged atoms larger than 2, then we can use a subscript to indicate the number. For example, if we have an hydride ligand, so this is the hydride ligand bridging 3 metal atoms, so we can use the prefix 3 here by the mu to indicate that this ligand is connecting 3 metal centers. And also, when we are writing the formula, we use the square brackets to indicate which groups are bound to a metal atom. So inside the brackets means that the chlorido and the amine ligands are bound to the metal atom, right? So, and then when we are writing the formula, therefore, we write the metal symbol first, then the ligands in alphabetical order. Because here, therefore, we have tetraamine, dichlorido, cobalt 3. So this order sometimes varies to clarify which ligand is involved in a reaction. And then when we have polyatomic ligand formulas, sometimes they are written in an unfamiliar sequence to place the donor atom closer to the metal atom. So to highlight which one is the donor atom. So for example, water, sometimes when used as a ligand, is written in this way in the complex to highlight that oxygen is the donor atom, and then therefore oxygen is forming the bond with the central metal atom or ion. Okay. And then when we have an ambidentate ligand, which can bind to the metal atom through different atoms in the ligand, then the donor atom can be specified by underlining it, such as in this case. And the ligands in the formula are in alphabetical order of binding element, and thus the formula and the name of the complex may differ in the order in which the ligands appear. All right, so based on this, let's try to give the names for all these complexes. Does anybody want to try the first one? Yes, no? Too confusing still? All right. So the first one would be tetraamine, G, chlorido, platinum, 4, right? Because we have 4, the oxidation state here for the platinum is 4. So from that table, actually, that I showed earlier, it's also important to note that here we have, I think we have, we can check for the charge of the ligands here as well, right? So the chlorido has a charge -1, and the amine ligand has no charge. So this way we can figure out by checking the charges as well from each ligand, what's the oxidation state of the central metal atom or ion. All right, this compound, okay? So remember, it's written on the alphabetical order of the donor atom, and then the name in alphabetical order here as well, right, of the ligand. So we have 3 carbonyl, so this is the carbonyl and this is the pyridine. So the carbonyl comes first. So 3 carbonyl, pyridine, nickel, 0. So here nickel is in the oxidation state 0. So this ligand is the ethylene diamine tetraacetato ligand, and then here we have chromate 3 as the oxidation state of the chromium, and then 8 because here we have an anion. All right, this one, therefore, like we have the chlorido ligand and then the 1,2-diaminoethane ligand. So the name is 2-dichlorido bis 1,2-diaminoethane cobalt 3. Finally, for this one, we have the carbonyl ligand and the iodido ligand. So the name is D-carbonyl, D-iodido rhodate, because here we also have an anion. Okay, so that's it, like for the nomenclature. Like, of course, we saw this like very briefly, but it's important that you guys know and familiarize yourselves on how the names and the formulas are written. This is important. So now we will talk about the main types of compounds in terms of the constitution and the geometry for coordination compounds. So the main coordination numbers and geometries that are possible and observed in metal complexes or coordination compounds. So when we are talking about the number of ligands in a complex, which are around a metal atom or ion, so this depends on the size of the metal atom, the nature of the ligands, and the electrostatic interactions that are present in the complex. So 3 factors dictate, therefore, the number or the coordination number of a complex: the size of the central atom or ion, the steric interactions among the different ligands, and the electronic interactions between the central atom or ion and the ligands. Therefore, as expected by intuition, a metal atoms or ions that are larger in sizes or that have larger radii, they would favor higher coordination number. So the larger size in later periods favor higher coordination numbers. And therefore, similarly, if we have very big or bulky ligands, then this would lead to lower coordination numbers because we would have a lot of steric interactions between the ligands, which are interactions by space exclusion, because if they are so big, we cannot fit many of these ligands around a metal atom or ion. Okay, so let's talk about like cases in which we can have low coordination numbers. So here, for example, coordination number 2 and coordination number 3. So two coordinate complexes are found, for example, for copper plus and silver plus. They form linear species. For example, this complex containing silver and 2 chlorido ligands. So this is responsible for the dissolution of solid silver chloride in aqueous solution containing excess of chloride ions. 2 and 3 coordination is relatively rare, actually, in metal complexes. So these are the examples for 2 coordination, and in the case of 3 coordination, this is found with very bulky ligands, such as in this example for as shown in this figure, in which we have this 3-cyclohexyl phosphine ligand, which is very bulky. So in this case, we can observe 3 coordination, but the most common case or most of the complexes are found or they are observed with intermediate coordination numbers, which refer to coordination numbers 4, 5, and 6. They are the most important class of complexes, and they include the vast majority of complexes that exist in solution in almost all the biologically important complexes. So let's talk about coordination number 4, coordination number 5, and coordination number 6. Okay, so starting with 4 coordination, 4 coordination is found in an enormous number of compounds, and basically we can have 2 basic geometries for 4 coordination: tetrahedral geometry and the square planar geometry. All right, so tetrahedral complexes having a tetrahedral, approximately a tetrahedral symmetry. So we have something like this, right? In three dimensions. So tetrahedral symmetry is favored over higher coordination numbers when the central atom is small and the ligands are large. And then another, so this is much better than my drawing, of course. And then another important geometry for coordination is square planar geometry. So these are the 2 most common or the 2 most important arrangements for coordination. So tetrahedral geometry and square planar geometry, in which we have 4 ligands surrounded by the central metal atom in a square planar arrangement. So these square planar complexes are rarely found for S and P block complexes, and then they are more common or abundant for D8 complexes of the elements belong to the 4D and 5D series. And for 3D metals with D8 configurations, this square planar geometry is favored by ligands that can form pi bonds by accepting electrons from the metal atom, and then we will see why very soon as well. Okay, so in addition to 4 coordination, another important intermediate coordination number is coordination number 5. Coordination number 5, they are less common relative to 4 coordination and 6 than coordination number 4 and coordination number 6. Because like 4 and 6 are the most common coordination numbers for metal complexes and coordination compounds. But after them, the 5 coordination is the more common one. And in this case, we can have a geometry that it's either a square pyramidal or a trigonal pyramidal geometry. So these are the normal or the ideal geometries for 5 coordination. So the distortions from these ideal geometries are common, because only small changes in bond angles are needed to change the structure to lead to an intermediate configuration, and then they can have very similar energies, so we can have this variety of distortions. So this trigonal bipyramidal shape minimizes ligand-ligand repulsions, but steric constraints on ligands that can bond through more than one side to a metal can then favor the square pyramidal structure. So here we have examples of this square pyramidal geometry here, in which this bulky ligand here forms this constraint and enables this square pyramidal geometry. And then here we have the trigonal bipyramid geometry around the central metal ion. So these are the most common ones. And here it is another beautiful representation of a square pyramidal type of geometry for 5 coordination, and here trigonal bipyramid geometry for 5 for coordination number equal 5. Okay. So after this, so we saw coordination number 4 and coordination number 5, and now we can talk about 6 coordination, or coordination number 6, which is the most common arrangement for metal complexes, and it's found on S, P, D, and more rarely F metal coordination compounds. We can safely say that almost all 6 coordinate compounds are octahedral or have shapes that represent small distortions of this perfect octahedral shape. So a regular octahedral arrangement of ligands is highly symmetrical, as shown here in this figure. And the simplest deviation of this octahedral symmetry is the tetragonal, and occurs when 2 ligands along one axis differ from the other 4. So we can have contraction or elongation along one of these axes in which the ligands are trans to each other. And then when we have, for example, D9 configuration, this tetrahedral distortion may occur even when all the ligands are identical, leading to the Young-Taylor distortion. And then when we talk about higher coordination numbers, we can have like 7 coordination, for example, for larger group 2 metals, a few 3D metal complexes, and much more like 4D and 5D, because they are larger, so they favor the accommodation of more than 6 types of ligands. And then like the different kinds of geometries also have like similarly in energy, so we can have a variety of structures, and these structures include pentagonal bipyramid, a capped octahedron, or a capped trigonal prism, as shown in this figure. And this is also observed for 8 coordination, in which we can have also a variety of different structures, as shown here in this slide. So these are the main points regarding these main coordination numbers, but we will be focused more on coordination number 4 and 6 for the discussion of electronic properties and on the discussion of bonding and electronic and magnetic properties. Another important concept is that we can have polymetallic complexes in which we can have more than one metal atom. So in this case, the metal atoms can be held together by bridging ligands or by the direct metal-metal bond. And then sometimes we also have the term metal cluster that is used when we have polymetallic complexes in which there is a direct metal-metal bonds between at least 3 species forming triangular or larger closed structures. And these polymetallic complexes can be formed with a variety of ligands. And then, for example, here we have a polymetallic complex of copper held together by acetate ion bridges. So we have the mu representing here that the ligand is binding or connecting two types of metal. And then this structure also in which we can have 4 iron atoms bridged by these types of ligands, for example. All right, so let's take a 10-minute break now. So let's get back at 1:11, and then we will discuss this. We will start to discuss isomerism and chirality. So actually, let's get back at 1:12 because it's 1:02 now. All right. So see you guys in 10 minutes at 1:12. Hello, everyone. Welcome to our second part of the lecture. So now we will discuss the occurrence of isomerism and chirality in coordination compounds. Okay, so when we are talking about coordination compounds and molecules in general, like a molecular formula by itself often does not give enough information to identify a compound unambiguously. So we can have the occurrence of isomers, which refer to compounds that have the same molecular formula, but different structural formulas. So we can have structural isomers, which differ on the connectivity among the atoms, and stereoisomers that have the same connectivity, but differ in the spatial distribution of atoms or groups in the molecule. So in terms of structural isomers that differ on the connectivity among the atoms, we can have, in the case of coordination compounds, linkage isomerism, ionization isomerism, hydrate isomerism, and coordination isomerism. So in the case of linkage isomerism, this occurs when we can have ambidentate ligands in which the same ligand may link through the metal through different atoms. So this type of isomerism, for example, accounts for the red and yellow isomers having this formula, in which here for the ligand, the attachment to the metal can occur either via the oxygen or nitrogen atoms. In the case of ionization isomerism, this occurs when the ligand and the counter ion in one compound can exchange places. So, for example, these two molecules refer ionization isomers. And then we can also have, similarly, the hydrate isomerism, which arises when one of the ligands here is water. So, for example, these two compounds are they have a hydrate isomerism because there is the exchange of places here between chlorido ligands in the first coordination sphere of the compound and the water. When we have coordination isomerism, this occurs when we have when there are different complex ions that can form from the same molecular formula. So here we have a cation and an anion, and both of them are complexes. So here, in this case, these two different coordination numbers are examples of coordination isomerism, because in this case, in one of the isomers, the metals in the complex change. So the combination metal and ligands change in this case. So when we have then, like when we establish which ligands bind to which metals and then through which donor atoms, we can then consider how we arrange these ligands in space. And then this can give rise to a variety of isomerism that can occur by considering the changes in ligand arrangement for each one of the common complex geometries. And this is known by the geometric isomerism. So this refers to the changes in which the ligands can be arranged in space. So this is the geometric isomerism, in which leads to the formation of these stereo isomers, in which we can have diastereo isomers, which are isomers displaying geometric isomerism, in which the different types of isomers are not enantiomers. And enantiomers refers to combinations of isomers in which one is not a mirror image or not overlaps with each other. And this leads to the observation of chirality or optical isomerism. Okay, so let's take a look on these geometric isomers or geometrical isomerism that can be observed for the common geometries for complexes. So when we are talking about four coordination, one of the geometries is the square planar complex. So if we have this kind of complex with this composition, for example, two types of ligands and two ligands of each type, we can have two types of geometrical isomers in which the ligands can be trans to each other, or the cis isomer in which the ligands are adjacent to each other. If we have this kind of composition, one ligand, then two ligands of the same nature, and another ligand, we can also have these trans and cis isomers in which the ligands have in the same composition here, which can be B, in this case, they can be trans to each other or opposite sides of each other, or they can be adjacent to each other. When we have four ligands that are different, then we can have, like, we can specify, for example, which ligand is trans to which, or which ligand is opposite to which. For example, in this case, we have A trans to D, in this case, A trans to B, and then in this case, A trans to C. So these are like different types of these geometrical isomers in this case. So in all these cases, we only have these stereoisomers. So the occurrence of enantiomers for square planar complexes is not observed. So we don't have enantiomers here, just the isoisomers or the geometrical isomers. So when we are talking about tetrahedral complexes, then the only isomers that we can have are the optical isomers or the enantiomers that are not superimposable mirror images of each other. So in this case, this occurs only when we have all four ligands are different, or when we have unsymmetrical bidentate chelate ligands in this case. So in here, therefore, the mirror image isomers usually make an enantiomeric pair, and then this gives rise to optical isomerism. So here, the formation of diastereoisomers isomers is not observed for tetrahedral complexes. So we don't have simply geometrical isomerism here in this case. So when we go to coordination number 5, we can have the main geometries as we discussed, the trigonal bipyramidal and the square pyramidal complex. And then these energies of these various geometries are often similar to each other, which means that in solution, the complex can change geometry very fast. So in solution, for example, a trigonal bipyramidal complex with monodentate ligands are often fluxional, which means that can twist and change into different shapes. So a ligand that is axial at one moment can become equatorial to the next. And then the conversion of one geometry into another occurs by a phenomenon called Berry pseudo-rotation, in which here we have a transition from bipyramidal to square pyramidal and bipyramidal geometries. Therefore, these, although isomers in theory could exist for 5 coordination, they commonly are not separate because not identifiable or not isolated, because in solution the geometries change, and we can have bipyramidal, trigonal bipyramidal turning into a square pyramidal and into a trigonal bipyramidal again, and this leads to the exchange in the position of the ligands, and this can occur fast, so it's not possible to observe in solution the different isomers. All right. But in this case, we would have, it's important to mention that both the trigonal bipyramidal and the square pyramidal complexes can have 2 different distinct sites, so equatorial sites and axial sites for the trigonal bipyramid, and the axial and basal sites for the square pyramid. All right, so now let's go to the octahedral complexes. So coordination number equals to 6. So in this case, there's only one way to arrange the ligands if we have all the ligands the same or when only one ligand is different. However, when we can have this type of composition in which we can have 2 ligands of one type and the 4 ligands of another type, then we can have that in this case, the B ligands can be into adjacent sites or opposite sites, leading to cis and trans isomers, as well as shown in this example here for this complex containing amine and chloridyl ligands. And when we have 3 ligands of one type and 3 ligands of another type, we can also have 2 geometrical isomers, because then there is also two ways to arranging the ligands. So in one of the isomers, the three A ligands can lie in one plane, and the B ligands can be perpendicular, lying in a perpendicular plane. So this is shown here in these images. So this is the mer isomer or meridional isomer, because each set of ligands can be regarded as lying on a meridian of a sphere, as shown here. And then we can have the fact that comes from facial isomers, in which the three A and B ligands can be adjacent to each other or occupying the corners of one triangular face of the octahedron. So this is the factial, and then this is the meridional isomer. So we can have these two types of geometrical isomers for the octahedral complex of this Ma3B3 composition. Then these things can start to be a little more complicated as well when we increase the variety of ligands. So for example, if we have two ligands of one type, two ligands of another type, and two ligands for another type, then we can have 5 different geometrical isomers, all trans, and then other 3 different isomers when one pair of ligand is trans with the other 2 are cis, and an enantiomeric pair of all cis isomers. Okay, so in addition to these many examples of geometrical isomerism for octahedral complexes, some octahedral compounds can also be chiral. And then in a very simple example is this acetylacetonate ligand with manganese, in which we can have like isomers, as this is bidentate ligand. So here in this case, we have that the isomers are not superimposable images of each other. So they are optical isomers. Okay. So in octahedral complexes, we can have both geometrical and optical isomers. Another important thing when we talk about coordination compounds refers to the thermodynamics of complex formation. So if we regard the complex formation, for example, here a complex of iron as the central metal atom or ion, or here as the central metal ion, forming a complex with this ligand, okay, thiocyanate. So if we regard the formation of this complex by the reaction of the ions here, or the reaction of the complex coordinated by water with the ligand, so we have the binding of the first ligand, the first thiocyanate ligand, to the coordination sphere of the iron. This can be described by this displacement reaction, in which the ligand displaces one of the water molecules acting as ligands here in this complex. So here we are considering the reaction of iron 3 with the ligand to give this species, okay? So this can be described by this equilibrium constant, and this equilibrium constant is called the formation constant of the complex. So here we are regarding like the formation of the complex as the reaction in which the ligand reacts with the metal ion, which is not isolated in solution but coordinated with water, and then here the ligand replaces one of the water coordinated with the metal, so that in this case the ligand becomes directly bound to the central metal ion, generating this species containing the ligand. So this gives an equilibrium constant, and this is the formation constant of the complex. And the magnitude of this equilibrium constant will indicate the strength of the binding of the ligand to the metal relative to the binding energy or the binding strength of water to the metal, right? Because the metal ions are not isolated in solution, they are coordinated by water. So the formation constant, therefore, will be relative to water as we are having this displacement reaction in which the ligand is replacing the water bound to the complex. So the equilibrium constant indicates the strength of binding of the ligand relative to water. So if the constant is large, it means that ligand binds more strongly than the solvent, water, to the central metal ion. And if the constant is small, that means that the incoming ligand binds more weakly than water. And then, like, these discussions of stabilities is more involved when more than one ligand may be replaced. So here, in this case, we can go to the case in which we have the formation of the complex here, for example, between nickel and ammonia, generating the hexaamino nickel 2 complex as shown here. And in this case, what we have is the replacement of 6 molecules of water in the coordination sphere of the metal by the 6 amine ligands, okay? So in this case, of course, we have 6 successive steps. So the first ligand is bound, then we have the second ligand, and so on until all the 6 amine ligands, for example, bind to the metal. So in this case, we can have a formation constant for each one of these successive steps. So we can have Kf1, Kf2, Kf3, and so on for each one of the successive binding of the ligands. So we can have this overall expression for the formation constant, okay, as shown here in this case, in which the overall formation constant is therefore the product of the individual formation constants. And then here we have the values for formation constants for this reaction for different types of ligands and different types of metals. And then, like, in general, we can observe that the stepwise formation constant typically goes into the order that the first one is bigger than the second and so on, because this is expected statistically, because the decrease in the stepwise formation constant reflects the diminishing statistical factor as successive ligands are replaced, right? So when the first ligand can replace each one of the 6 waters, but then the second ligand can only replace each one of the 5 waters, the third ligand each one of only 4 waters, and so on. So this is what the diminishing statistical factor refers to. And then this is also coupled with the fact that the increase in the number of bound ligands also can increase the likelihood of the reverse reaction. And if we have a major deviation in this trend of Kf1 higher than Kf2 and so on, this may indicate a major change in the structure. So I mentioned the chelate effect earlier in our lecture. So the chelate or macrocyclic effect this occurs when we have polydentate ligands, and this refers to the greater stability of complexes having these polydentate ligands as compared with a complex having the equivalent number of analogous monodentate ligands. And this occurs, this scalate effect or this increased stability for the coordinated polydentate ligands occurs because this is largely an entropic effect in which uh, in addition to the to an additional entropic contribution, however, like the most contribution comes from entropy changes. So when we consider KF1 for the formation of a complex with a bidentate chelate ligand, such as the 1,2-diamino ethane, and then we compare with the value of beta-2 for the corresponding bis amine complex, or the complex having two monodentate amine ligands, we can find that the equilibrium formation for this for the coordination of this ligand versus two amine complexes, this one gives rise to a much higher constant of formation. So here, so why this happens? Because in both cases, so here we have an example in which we have the formation of these complexes in which one of these bidentate ligands binds to the cadmium ion here in this case, leading to this complex, and then in the case in which two amine molecules bind to the cadmium atom in this case, generating this complex. So here we have the monodentate ligands, and then here we have the polydentate ligands. So in both cases, the cadmium nitrogen bonds, similar cadmium nitrogen bonds are formed in each case, but even then, the formation of the chelate containing complexes is more favorable and has a higher constant. And this greater stability, like we can see that while the enthalpies are similar, there's a large variation in the entropy of the reaction. And this is what gives rise to this difference. And this greater stability, therefore, of the chelate complexes compared with their non-chelate analogs, this is called the chelate effect. And this is traced primarily to these differences in the reaction entropy between the chelated and non-chelated complexes in dilute solutions, as we saw here in these expressions. And then when we have the reaction of chelation, we have an increase in the number of independent molecules in solution, while the non-chelating reaction, there's no change in the number of independent molecules. So we can see here, we have two molecules leading to three molecules, and then here, three molecules leading to three molecules as well. So here we have an increase, a larger increase in entropy. So this leads to a more positive reaction entropy and a more favorable process, because this gives rise to a more negative Gibbs free energy that has contributions from enthalpy and entropy. And the entropies measured in solutions support these observations. So this entropy advantage of chelation extend beyond bidentate ligands and applies to any polydentate ligands. And then, as expected, the greater the number of donor sites that a multidentate ligand has, this means that it has a greater entropic advantage of displacing the monodentate ligands. For example, macrocyclic ligands, where multiple donor atoms are held in a cyclic array, such as chrome-neutral or phthalocyanins, they give complexes with greater stability than what would be otherwise expected. And and then in these types of molecules as well, we also have additional contributions from energy to give even greater stability that comes from the pre-organized nature of these ligating groups directly to the central metal atom. And then in this case, this is also referred as the microcyclic effect as well, when we also have this pre-organization of the ligating groups in this type of molecule. Okay, so far, therefore, in this first introduction part, we talked about main concepts, nomenclature, the main coordination numbers, constitution and geometry, examples of isomerism and chirality, and we talked briefly about the thermodynamics of complex formations with trends, information constants, and the catalytic effect. Okay, all right, so for the remaining time of our lecture, let's get started on the discussion of electronic structure and properties of complexes. So the idea is that we will discuss the electronic structure, we will talk about the main theories that are employed to explain electronic structure and bonding in coordination compounds, which are the crystal field theory and the ligand field theory. Then we will discuss how these theories are very useful for the interpretation of electronic spectra and electronic properties, as well as magnetic properties or magnetism. So I have mentioned that the d-metal complexes and coordination compounds play a very important role in inorganic chemistry. We will discuss the bonding here in these compounds using two models. We start with a simple but very useful and beautiful model, which is the crystal field theory, which is based solely on an electrostatic model of bonding. And then we will progress to a little bit more sophisticated theory, which is the ligand field theory, which starts to consider a little bit of covalency in the formation of these bonds. And both these theories invoke a parameter, which is the ligand field splitting parameter, to correlate electronic properties with spectroscopic and magnetic properties. So when we are talking about the electronic structure of d-metal complexes or coordination compounds, we have two main models, the crystal field theory and the ligand field theory. So the crystal field theory has emerged from an analysis of the spectra or the electronic spectra of d-metal ions in solids, and the ligand field theory arose from the application of molecular orbital theory to metal complexes. Therefore, like using these analogies or these concepts, we can say that the crystal field theory is more primitive or more simple, but capture the essence of the electronic structure of the complex, and then it is straightforward, while the ligand field theory builds on the crystal field theory, so advances the crystal field theory to give a more complete description of the electronic structure of the complexes, and then accounts also for a wider range of properties. So let's start to discuss the crystal field theory. So here, in the crystal field theory, we use simply an electrostatic model to describe the bonding, in which the lone pair or the electron pair from the ligand is regarded as a point negative charge, and this point negative charge from the ligand lone pair repels the electrons of the central metal ion or ion, so repels the electrons located in the d orbitals of the central metal ion or atom. Therefore, the ligand lone pair, electrons from the ligand, from each ligand is modeled by a negative point charge, and this negative point charge therefore repels the electrons in the d orbitals of the central metal ion. This is the essence of the crystal field theory, because therefore the theory concentrates on the resultant splitting of the d orbitals as a result of this repulsion by the lone pair of the ligands into groups of different energies. So the theory concentrates on the result splitting of the d orbitals of the metal ion into groups with different energies. And this splitting is used to rationalize and correlate the optical spectra, thermodynamic stability, and magnetic properties. So we will talk here for octahedrals, for complexes having octahedral, tetrahedral, square planar, and tetragonally distorted geometries, okay? All right, so let's start with octahedral complex. So in an octahedral complex, we have the metal surrounded by 6 ligands, okay? So we have the metal. If we are regarding the lone pair from each ligand as a negative point charge, we have 6 negative charges in an octahedral geometry around the central metal ion or atom. So we have 6 negative charges representing the ligands that are placed at points in which in an octahedral array around a central metal ion. 6 charges distributed in an octahedral geometry around the metal ion. So these charges, negative charges, are the ligands. According to the theory, they will interact strongly with the metal cation. And the stability of the complex will come from this, because they're negative charges, ligands, they interact strongly with the metal ion, which is usually like a cation, or having being electropositive. So the stability of the complex, so this will give a strong interaction, and then the stability of the complex will come in large part from this attractive interaction between the opposite charges. However, in the metal ion or atom, the electrons will be in different types of d orbitals. They will be in the d orbitals. The valence electrons will be in the d orbitals. And then the electrons present in different d orbitals will interact with the ligands in a different way or to different extents. And this changing interaction of the d orbital, of the electrons in the d orbitals of the metal atom or ion with the ligands, this is what will give major consequences to the properties of the complex. So what happens is, if we draw here a graph of energy, right? And then we draw here the d orbitals for a symmetrical, for a metal cation, or for the metal species, for example, for the central metal ion, or the central metal atom or ion, for example. So when we have octahedral arrangement of negative charges around this central metal ion or atom, what happens is the d orbitals of the metal. So we have 5 d orbitals, right? So the d orbitals in the metal atom or ion will be repelled or will interact differently with these 6 negative charges, or these negative point charges represented by the ligands. And this will lead to the splitting of these d orbitals into 2 groups, or two energy groups, in which here we have the dz square orbital and the dx square minus y square. And here we have the dxy, dxz, and then dyz orbitals. So when we have a metal ion, there it's free. And then when we have an octahedral arrangement of negative charges around this central metal ion or cation, we have the splitting of the d orbitals into different groups of energies in which follow this pattern for the octahedral geometry. Okay. So why this happens? So actually, we can understand this by taking a look about like how the different orbitals are positioned in the metal atom, and considering how we can place these ligands around the central metal ion. So here we can, if we have, for example, the different axes, for example, X, Y, and Z, for example. Yeah, this is not good because I messed it up. Z should pass here. Yeah, okay. So if we have the 3 axes, we can consider that let me try to draw this again. So if we have the 3 axes, for example, X, Y, and Z, and we consider the central metal atom to be in the origin, we can approach placing these 6 negative charges in an octahedral geometry around the central metal ion by putting them at the top of this axis, as shown here in this image. So we have the X, Y, and Z axis, and then we see that the point charges are positioned directly along the axis. So here in this approach, we have the 6 negative charges along the X minus X, Y minus Y, Z minus Z. Therefore, if the ligands are positioned directly along the axis, the orbitals that are oriented directly along X, Y, and Z, they will be more strongly repelled by the point charges of the ligands than the orbitals positioned in between these axes. Therefore, electrons in the dz square and dx square minus y square, which are the orbitals that are along the axis, they will be more strongly repelled by the electrons of the ligands than the electrons in the dzx, dyz, and dxy, because these orbitals are concentrated in the regions in between the axes. So this electrons in these orbitals will be repelled more strongly by the ligands, and they will have the energy. They will have the same energy in the octahedral environment, and then they will have this EG symmetry. And these orbitals will be lower in energy relative to these orbitals. And then in this case, they will have a T to G symmetry. And then also here, they will have the same energy among each other. And then here, they will have the same energy among each other. So here we have the metal in a totally spherical environment. Therefore, when we have an octahedral environment, then we have the splitting of the d orbitals into two levels of energy. Here we have more strongly repelled, dz squared, dx squared minus y squared. And then here we have the set of orbitals that have their positions in between the axes. So this corresponds to dxy, dxz, and dyz. And then the energy separation of the two sets of orbitals is called the ligand field splitting parameter, in which this O means octahedral field. And the energy level here that corresponds to the hypothetical spherical symmetrical is the barycenter of the levels. So the two EG orbitals lie at 3/5 of the ligand field splitting above the barycenter, and the three C2G orbitals lie at 2.5 times the ligand field split parameter below the barycenter. So if we take a look at the absorption spectrum of this complex of titanium-3 and water, we can already see the interpretation of the electronic spectra using this very simple model, in which this absorption here refers to the excitation of the electron from this level to this level, generating this band, which would not be expected if all the electrons or all the d orbitals would have the same energy. Okay, so I think we can stop here for now, and then we can continue in our next lecture next Friday. So we will continue this discussion of electronic properties of complexes by the crystal field theory and ligand field theory. Okay, so anybody has any questions before we wrap up? If not, thank you very much, guys. I will see you next Friday.